Hello, I'm Alla Balueva from University of North Georgia, USA. So taking the opportunity, I want to thank organizing committee and Professor Ricavelli, Vittorio, for nicely organized conference and giving us opportunity to present remotely. So that is a joint research of University of North Georgia, USA, and Institute for Problem in Mechanics of Russia Academy of Sciences. So research started in 2019 when it was initiative from NSF about joint proposals on bio nanotechnology from Russia and USA. So we started thinking what can be done. And our colleagues from Moscow, they found here in US company, Biotech, who invented new innovative bio nanocoatings on dental implants. So these coatings are made of the tricalcium phosphate material, which is close to the bone structure. Because of that, the healing process is called osseointegration. When bone ingrows into coating, increases from 3 months to 3 weeks, which is a great breakthrough. So since that coating was on nano level, we thought we can apply here atomistic calculations. So the next, we did this work fully from scratch. We started, our students started doing research of their publications, and we found out that there are cases of detachment of this coating in future. It means like in 2-3 months. That prompted us to start this investigation of adhesion strength. And we decided to model this chemical reaction between tricalcium phosphate, which is here, and titanium, that material of the dental implant. So, and we had no idea at that time how we're going to calculate the strengths. So everything just was going, yes. So since it started in 2019, so we already had several publications about this, and we calculated already binding energy of tricalcium phosphate. But now we discovered that there are already more new coating doped with silicon. So it means here when phosphate is replaced with silicon, so osseointegration even greater. But the question arises, will the adhesion of this new coating doped with silicon be the same good as adhesion of tricalcium phosphate? So we decided to model this reaction of this silicon trioxide with titanium to see if binding energy or adhesion strength is greater or less. So till the end, we didn't know the answer. We were very intrigued what's going to happen. So here we used density function theory, and actually that is the method. So actually all these calculations of chemical reactions on atomistic level became possible with invention of density functional theory. It was invented in 1964, pretty recently. So that is, we need to solve Schrödinger equation, a little bit like basic, because that will help to understand what's done. So, and Schrödinger equation, that is equation for many particles. So here, kinetic energy of electrons, nuclear, nuclear, electron, nuclear, nuclear, electron, electron, column interactions. So that is many dimension equation. So it's not possible to solve this even with modern computers in general form. So first approximation of density function theory is called Bohr-Oppenheimer approximation, where we neglect kinetic energy of nuclear. So we believe that nuclear much heavier and they move much slowly compared with electrons, and we believe the kinetic energy is zero. So it means all processes are happening at the absolute zero. Every time we set up the system at the ground state energy level, it means at absolute zero. So the next approximation of density function theory, and then the main approximation, so it means now we have 1, 2, 3, 4 terms left. So still partial differential equations, and we need to solve this for wave function, and means for dimension of this for each particle. It means dimension of this equation. If, for example, even we have 4 nuclei, just 4. It means electrons around, for example, 6. 4 times 6, 24. 3-dimensional times 3. 24 times 3, 72. So it means 72-dimensional problem, partial differential equations, not possible to select, it's not solvable. So what suggested founders of density function theory? We multiplied the equation for Xi from left-hand side, right-hand side. And this way, we have here that is normalized wave function squared. So, and that is 1. And we have here E just left. And here we have some functional phi squared. So we know that phi squared is probability that electron in some space. So it means here they moved from Xi to electronic density. So it means our right-hand side, now E left, here on the left, and here right-hand side transformed in terms already raw electronic density, where we have Xi squared. And that is already a 3-dimensional problem. So it means from 3n dimensional problem, we move here to 3-dimensional problem. So that means since we need to find E in ground state energy, we need to find minimum. We need to find rho for which E is minimum. So it means we need to find minimum of quadratic functional with respect to rho. And that still 3-dimensional problem is very difficult, very sophisticated problem. Because of that, during our calculations, sometimes it didn't converge to the local minimum on potential energy sources, converged to a different point. We need to start it over. So these are 2 founders, Hockenberg and Kochen, 1964. So these are their main theorems. So actually, what that already we got when we did our research, what to do, how to find binding energy of the coating and substrate. So first we set up reactants. It means our tricalcium phosphate, for example, and titanium to ground state energy on potential energy sources. So next reaction occurs till the maximum, that is activation energy. And next these products go back, already reaction occurs, no new bonds formed. And again, products here goes to the stable position on the potential energy surface local minimum. So we find here ground state energy for products. And next, energy of reactants, energy over products, always less than energy of the products. Why? Because some energy went to bind these materials, to form new bonds. And that is binding energy. That's exactly what we calculate. First for one coating, and next for the second coating, to compare the adhesion strengths. So the next, I'm going to move to calculations. So we're going to set up each elements of our reactions to ground state energy. And next, we're going to set up to ground state energy products. So that binding energy, energy of the, actually of reactants, minus energy of the products. So results, moving to the results. So it means we used here quantum mechanics package Gaussian for calculations to set up each structures to ground state energy with Becky 3-parameter Liang-Park functional. So, and that is already our setup. So it means first constituents of the tricalcium phosphate to stable position. Next, silicon trioxide to stable position. We calculate ground state energy. So next, we add here reaction with titanium, ground state energy of both. So the next, we add at the end, at the top, one more phosphate here, phosphate PO42, one more silicate trioxide. So here, that is our phosphate, part of the coating, one more phosphate. Here, oxygen, red atoms, oxygen, oxygen, oxygens, four oxygens here as well. That is our titanium in the middle. So titanium was at the beginning 2+. the charge of titanium was 2 plus. Now we can see the charge of titanium 0.558. It reduced. Why? Because here electrons from oxygens moved here to 3 orbital spaces for titanium, and that how its charge decreased, and that how the bonds formed. So more electrons go here to titanium, the stronger bond. So we have the same charge of titanium here decreased from 2 plus for silicon. So that titanium gray atom, and here that silicon and silicon trioxide. So, and next we added here at the end 3 calcium green atoms, calcium 1, 2, 3. So we see here that charge of titanium went from 2 plus 0.563. And when we do doped coating, it went from 2 plus to negative 0.334. That means more electrons here, in this case of silicon, doped silicon, moved to the titanium. Stronger bonds here. Besides, when we have this atom became negative, that was very interesting for us. That means here we have ionic bonds as well. So it means attraction of this big negative atom, titanium, and big here atoms, silicon and calcium, which are 2 plus, they are positive. So it means crystal structure here formed, and we see even from the picture that binding energy here is greater for doped silicon. And that was confirmed by calculations. So here binding energy, energy of the reactants, ground state energy minus energy of the products. For tricalcium phosphate, initial coating is 0.492 atomic units. And for calcium doped with silicon is 0.94 atomic units. It's greater. It means use of silicon is justified, not only from the point of view of osseointegration, but also from point of view of adhesion strength. So the next question that we raised, that is binding energy microscopic characteristic. We can compare this experiment. How to move from microscopic to macroscopic characteristics of adhesion, which is critical surface energy. That method is developed by Professor Dashevskiy, so that is our co-author. So here, the main idea. So we believe that each atom of titanium is connected with each atom of, for example, tricalcium phosphate. And we found binding energy of unit cell from atomistic calculations. To calculate here critical surface energy, which is binding energy of unit surface, we need to multiply this binding energy of unit cell by number of unit cells. So how to calculate number of unit cells? So that is here. So if we have molar mass and we divide them of tricalcium phosphate and we divide them by Avogadro number, we're going to get here little mass of the molecule of tricalcium phosphate. So if you have density of tricalcium phosphate, that is mass per unit of volume. So what is mass per unit of volume? This little mass of molecule times number of molecules. Little mass here and here cross out, we get here number of molecule per unit of volume. So the next, we take cubic root and we square it. And this way, we got average number of molecules per unit of surface. So that formula we're going to use on the next page to calculate here critical surface energy first for calcium phosphate, tricalcium phosphate, and that's 6.927 joule over meter squared. See here already units, not atomic units, because atomic units for unit cell 0.492, we converted to joules, that conversion factor. Next by number of unit cells, and that number. So that is 6. And next for doped material, we got 14.464 is greater. So it means from all perspectives, unit cell, like a binding energy or like characteristic macroscopic characteristic adhesion of doped silicon is greater. So that I conclude our research on that. So it means here we did some atomistic calculations of 2 coatings to compare the adhesion and using of silicone as doped material for tricalcium phosphate is justified not only from osteointegration, but also its adhesion strength is greater. Thank you very much for your attention.